Florida coast. Your traffic is a little slower than, or a little better than ours. Ours is very slow. But of course, now you have the Grand Prix out here, so things are a little dicey right now. So I want to give you an overview of what we've been doing from research aircraft for basically the past 15 years. I want to make it clear that I started this when I was 25 years old, okay? For the last 15 years, and you know. Basically, the folks we work with are just across the bay over here at MacDill, the hurricane hunters with NOAA. So we try to get out there at least once or twice a year out on the P3 and get some measurements in both fluids simultaneously, both atmosphere and ocean, to really try to begin to understand the delicate coupling that's going on between the two fluids. This gets and begs the question, does the ocean matter for tropical storm intensity? Now, since you're all oceanographers, most of you are oceanographers, I'm sure what your answer is, but when you try to convince the meteorologists that the ocean is really important, it's sort of 50-50. So the big signals for the Gulf are right over the loop current, so that's why we like to measure it and understand it, not only under strong wind conditions, but also like what occurred during Deepwater Horizon. You know, where we went out and made 10 to 15 research flights to document where the loop current was, because there was some belief that if oil got entrained into the loop current, it could end up, you know, in the express lane down to the Florida Keys or somewhere along the eastern seaboard, up until that time that Eddie Franklin pinched off. So I'm going to give you an overview of this. A lot of the work is because of my strong research team. And the students do a large fraction of the work. They get their hands dirty and get into the data. It's great to be over and on the aircraft and get students involved in this type of measurement program, so they begin to understand how to acquire measurements from the airplane. A lot of folks have funded us over the years. NOAA, NSF, NASA, and Deep Sea was a GOMRI-supported consortium up until the last year. And the one over here to the left is the Department of Interior, called Minerals Management Service. It's now called BOMET. That's French for MMS. But they've provided some funding for us to do this type of work too during tropical cyclones. Okay, how do I advance?
You need one of your students.
Yeah, I need a student. There we go. I'd like to say that we have figured out the landfall problem. As you recall, during the tumultuous 2004-2005 season, we had 7 or 8 landfalls in Florida. So we decided we're going to move Florida back up here. Technological difficulties today. So Florida's now up in here, so prepare for cold weather. So I'm going to motivate the discussion, talk a little bit about ocean response characteristics. A lot of the ocean response characteristics were done back in the 80s when folks didn't really initialize ocean models with realistic ocean conditions. And having realistic ocean conditions in ocean models, modelers will tell you that becomes really important in the problems. So I'll talk about Isidore and Lily, which was just right around the turn of the century, 2002. Katrina and Rita. A little bit on Gustav and Ike and Isaac. Isaac was a storm that we studied under the GOMRI support through Deep Sea. And then the cold core eddies, like thin mixed layers, were an example for Hurricane Ivan, where we were fortunate enough to work with the Naval Research Lab. They acquired great data set right underneath Ivan, right at the shelf break between the DeSoto Canyon and onto the shelf in the northern Gulf. And I'll summarize it. But a recurrent theme is you you need ocean observations if you're going to run ocean models, okay? If you're going to try to characterize the ocean, you just can't, you need the ocean model and the ocean observations together to really begin to understand the problem. So, tracks of Katrina and Rita. So this is a motivating slide. Basically, you have all these rigs in the northern Gulf of Mexico. And I think roughly 35 to 40% were destroyed after the passage of both Rita and Katrina. Now the irony here is that when meteorologists looked at these two storms, okay, so here's Katrina that cut Dade County basically in half, made its way into the Gulf of Mexico, and then made landfall up here very close to New Orleans and Lake Pontchartrain. The conventional wisdom, since this second hurricane is following essentially the first hurricane, there's going to be a huge cold wake along here. So you don't really have to worry about the ocean. Well, that's so well and good if you don't have a loop current. If you have a loop current, that loop current doesn't cool significantly, and guess what? There's just more heat for the storm, for that second storm. So you got to know the 800-pound gorilla for hurricane intensity forecast in the Gulf is knowing where the loop current is and knowing where the warm and the cold core eddies are. And of course, once we had those two storms, we knew we had pain at the pump. So this is the ocean heat content product that was developed several years ago at the Rosenstiel School. And ocean heat content from space. The reason we're doing it from space is we can't be out there on aircraft all the time making measurements. It's just really costly. So you bring in satellite altimetry, you bring in sea surface temperatures, you bring in climatologies, and you come up with ocean heat content. Our product now is operational up at NOAA NESDIS for the North and South Pacific Oceans as well as the North Atlantic. It's an evaluated product that brings in all sorts of in situ subsurface measurement platforms like gliders, floats, time series from moorings, as well as perhaps drifters and XBT transects. That's another story on a different day. But the point is that when you begin to combine them, you see where here's the loop current, here's the path of Katrina, and right around this area between the loop current and the warm core eddy, you can see where the storm really got wound up explosively deep into Cat 5, and fortunately for the residents of the northern Gulf, it decreased to Cat 3 prior to landfall. Now, when you look at the SST image, you don't see a whole lot of the loop current in this type of image from TMI. So when forecasters look at just the SST, sometimes it's very difficult to figure out where the boundaries of the loop current are. So that's why having a product that shows warm and cold for a forecaster who has to make a decision very quickly, doesn't have hours to elaborate and look into all the different types of analyses, having something that shows warm and cold water or heat reservoirs versus cooler sinks is valuable. So there's the warm core ring, there's the loop current, and there's the Florida current going through the straits. So the big question is SST enough? And of course in 2005 we had the trifecta. We had Katrina, Rita, and Wilma, all Category 5 in one basin for the first time. So you had very strong Category 5 storms that interacted with the loop current primarily and the warm core eddy field. Now, what's the issue? When you look at cold cyclones in the water, like cold core rings, what's peculiar? Well, they have a relatively shallow mix layer, typically about 20 to 25 meters. Underneath is the thermocline. That goes down to about 80 to 90 meters. And when you calculate ocean heat content, this ocean heat content is probably about 6 to 10 kilojoules per square centimeter. That's not a lot of heat. By contrast, when you look at the warm core eddies of the big anticyclones, the depth of the 26-degree water, 122 meters beneath the surface. We can do this from space now using satellite altimetry. Mixed layers about 60 to 70 meters, and then the depth of the 20-degree isotherm is down around 250. So what this represents is about 115 to 120 kilojoules per square centimeter. That's a sizable amount of heat that's available for the storm. We're not saying that the storm sucks up all that heat. What we are saying is that it's important to know where that heat is located relative to the track, because it does make a difference in the forecast. Now, all of this is really important stuff, understanding where these sources and sinks of heat are, but it's equally important to understand the ocean's momentum response, because the ocean's momentum response significantly differs from, say, Gulf common water and these cooler cyclones versus the warmer anticyclones and the loop current itself. So here's a schematic, a cartoon, a typical hurricane, if you will. You get upwelling underneath the track. Over here to the right, typically 1 to 2 radii of maximum winds. You get strong shear. Lots of shear in the ocean is bad for the hurricane, so pray for ocean shear, because ocean shear causes mixing. If it causes mixing, it causes the SST to cool. If it cools the SST, the moisture and heat fluxes going into the storm are diminished. By contrast, you don't get this type of shear in the loop current itself. Why? There's a number of reasons. First and foremost, the strong near inertial currents that we see generated by hurricanes in Gulf common water and away from the boundaries, you do not see them in the loop current itself, simply because the strong advective tendencies of the loop current and its 1 to 1.5 meter per second currents essentially arrest that strong near inertial shear being generated. We'll see this in a case with Hurricane Lily and Isidore. Now, underneath the storm, you get the strong heat flux, and of course here's the wind going into the board and the wind coming out of the board. But the point is that this near inertial shear, and when you look at it, when you're looking at it from above, you actually see a nice clockwise rotation of the current vector as these packets move into the thermocline. And I'll give you a nice animation of this in a few minutes. So, relevant scales for the ocean response. And I only put a few up here, in particular Lily, Ivan, Katrina, and Rita. But some of the most important ones are the baroclinic phase speed. So when the baroclinic mode phase speed of the first baroclinic mode exceeds that of, so when U sub k over C over the first baroclinic mode phase speed, if this is more than 1, you typically see more of a baroclinic response. When this is less than 1, it's more barotropic. In this case, these are all baroclinic responses. The other key parameter is how fast the storm is moving. Now, meteorologists say, well, if the storm is moving so fast, then we don't have to worry about the ocean. Well, that doesn't make sense. You don't have to worry about the ocean response as much, but the ocean's still providing that heat flux. Even if the storm is moving a little faster, it's still picking up the heat and the moisture. Where's that heat and moisture coming from? It's not coming from a landmass. It's coming from the ocean, still being pulled up by the strong updrafts and the fluxes associated with the hurricane itself. The other key issue is this tau max, which of course gets into the whole idea of surface drag coefficients, which remains an open question. How strong are drag coefficients in 40, 50, 60, 70 meter per second surface winds? That's still an open question. So, this is what we did for Isidore and Lily. I want to highlight this. So all these measurements are being made by dropping a series of AXBTs that I'm sure you're familiar with, but we also drop AXCPs, An AXCP is an airborne expendable current profiler that goes down to 1,500 meters and sends data back to the aircraft for temperature, U, and V components of velocity, which is really important. This technology was developed by Tom Sanford at the Applied Physics Lab. He put them in XCPs, which you can launch from ships, but he also did some work with the oil companies where they actually put them in airborne canisters, where we now can throw them out of the aircraft and get data coming back to the aircraft for the current profiler, which is really where the momentum is really important. So on the 18th of September for Isidore, so we're going to take Isidore first, we were sort of saying, okay, we thought the track was going to come right through the straits and up into the Gulf, so we hedged our bets. So we went back and forth across the Yucatan Strait, coming south and doing this grid pattern. Of course, what did Isidore do? Isidore went a little to the right of the grid and then cut right back through the Yucatan Straits and then wound down over here in the Yucatan Peninsula. But on the 19th, we thought, okay, so the storm still hasn't come through at this point. We're going to hedge our bets and do this big pre-storm grid in the Gulf. And again, what did Isidore do? Just hung a quick left and then went over here. So this is what makes it a challenge. You have to have a good forecast, a good track forecast. And we know good track forecasts out to 2, 3, 4 days sometimes can have a lot of error in it. So you got to take that into account. But we did take the storm. We had a number of in-storm flights using the 2 NOAA P3s. The different symbols represent BT, CPs, and we can do CTDs from the aircraft. And the CTDs work quite well. So you can see that we really did a nice job in capturing what was going on with Isidore moving across the Yucatan Strait. And then normally what we do is we go out a day or two later and we try to make the measurements of the post-storm. So these are some post-storm measurements. We didn't want to get too far up in here because it's a very shallow shelf up here in this region just north of the Yucatan. So then what happens is that a couple days later, we still did this post-storm, but a couple days later, Lily was coming through. I'd like to say that we knew Lily was coming through when we did this grid, but that would be the full Pinocchio because we had no idea that Lily was going to follow Isidore. It turns out that a lot of times you have these tandems in the Gulf of Mexico. 2 strong storms essentially following each other. We saw it in 2002, we saw it in 2005, we saw it in 2008. We haven't seen it recently, but we'll see what happens this year.
The same in Atlantic, they also
Yeah.
in the Atlantic. They have the same picture.
Yeah. Well, it's because of the upper level steering currents. I mean, that's what's driving the path of the storm. So with Lily, we went back out and we did this in-storm with one of the airplanes, and then we went back to the wake, or the first wake experiment, and did another grid. Why do we do pre, during, and post? Is because it gets back to this whole idea about heat. How much heat is being lost, and how is it being lost? Is it being lost through vertical mixing? Is it being lost through heat transfer to the atmosphere, or is it some sort of a horizontal advection? That's why you need currents, temperatures, and salinities to give you that type of information. You can't just do it with an AXPT. And this is an example of what the radar image looked like as Lily was really spinning up. She was a Cat 4 over the loop current, and then fortunately for the state of Louisiana, she de-intensified to a Cat 1 just prior to landfall. So this is what the wind fields look like. This is from analysis that's done using the step frequency microwave radiometer that are on the P3s to give you near surface winds. This is for Isidore. This is for Lily. And what we did here is we computed the sensible and the latent, the momentum flux, as well as the enthalpy. Enthalpy is just A plus B. So enthalpy includes both the sensible and latent heat, and you can see here that we're probably up around 1.2 to 1.4 kilowatts per square meter, which is a lot of heat. That's a big heat flux. But you typically see these types of numbers when you go over the loop current and the warm eddies. So it's not just that the ocean isn't really significantly mixing. It means that that source of heat is available for the storm and it's sustained. So it's not just like a delta function, like here's heat and then it's gone. But as it moves over the loop current, it just keeps feeding it more and more heat. So it's not just circumstantial anymore. We have data to show that knowing where the loop current is really important in this problem. So this is what an example of what the Isidore data look like, and you can see where the upwelling, so this is pre-storm temperature and this is post-storm temperature. You can see the upwelling that was occurring over the Yucatan Shelf. And you can see over here, more than 4.5 degree cooling. In the Yucatan Straits, the cooling was about 1 degree C. So if it was 29, it's now 28. Or if it was 30, it's still 29. 29 is a lot of heat. Over here, it's decreased down to about 26 or 25 degrees Celsius. So if we go back to that, so this is a transect from B to B prime of what was going on during Lily. And so this is a profile of demarcation. This is about where the loop current ended. And up north of there, you can begin to see that really cool near inertial rotation. But down in the loop current itself, all we're seeing is very strong currents trying to get out of through the Florida Straits and into the Florida Current. And below, basically what we do, of course, is once you have velocity and velocity shear and the buoyancy, you can calculate Richardson numbers. Richardson numbers below a threshold value means the ocean's going to mix. Well, in our area, basically it was above 1 or 2. So the ocean wasn't significantly mixing in this area, which gets back to what I alluded to earlier. No mixing means more heat for the storm. So the data are really beginning to show that what we've been saying for 15 years is correct. And this is just accentuated a little bit more with a higher resolution. You see the nice near inertial rotation, and then down in the loop current, there's no near inertial wave.